Hello everyone, welcome to the series of video tutorials on the course Calculus and Numerical Methods. This is part 2 of the first chapter, the real number system, and the title is Upper Bounds and the Supremum. Outline of this video: upper bound of subsets of R, supremum of subsets of R, and examples of supremum and the upper bounds. So I will start with one simple example of a set. Okay, so let's say supposing I have a set A whose elements are, let's say, 1, 2, 3, 4. Let's take a simple set. Okay, now let's make one observation. Okay, this element 4 which is there, it is bigger than or equal to all the elements of the set, if you notice. Okay, so the number 4 is bigger than or equal to 1, the number 4 is bigger than or equal to 2, the number 4 is bigger than or equal to 3, and the number 4 is bigger than or equal to the number 4 itself, right? So the number 4 there is bigger than or equal to each and every element of that particular set. Why only this 4? If you pick up any number which is bigger than 4, which is not even there in the set, even that number is bigger than or equal to every element in this set. For example, if you pick up say 4.5, even this number 4.5 is bigger than or equal to every element of the set A, right? So 4.5 is bigger than or equal to x for every element x in A. Again, if you pick up one more number, say 50, even that is bigger than or equal to x for every x in A, right? So we have some numbers now, some real numbers, which may or may not lie in a given set, okay, and they are bigger than or equal to every element of that particular set. All right. So that such numbers are called upper bounds of the given set. Okay. So the number 4 here is an upper bound of this set. The number 4.5 is an upper bound of this set. The number 50 is an upper bound of this set. Okay, so let me put down the definition of upper bound of a set. Upper bound. So supposing I have a non-empty subset A of R. Okay, so let capital A be a subset of R which is non-empty. Okay, let capital A be a subset of R which is non-empty. Then a real number alpha is called an upper bound of the set A if alpha is bigger than or equal to x for every x in A. Okay, so such a number alpha is called an upper bound of A. A real number alpha is called an upper bound of A if for all x in A, alpha is bigger than or equal to x. Okay, now this capital A set here is an arbitrary subset of R, so it can be anything. So if you look at the upper bound, idea of upper bound geometrically, it means this. Supposing I have the real line, okay, and on this real line I will mark the set A. Let's say the points which I'm marking in red, let's say those are the points of A. Okay, A is an arbitrary set. I don't know which elements are there in A. So supposing the points which I've marked in red is my set A. Okay, so I will write the set A in red itself here. So that's my set A. Okay, now by a upper bound of this set, I mean a real number which is bigger than or equal to every element of this set. Okay, so geometrically speaking, that number which I'm talking about now, upper bound alpha, that has to lie on the right hand side of each and every element of A. Then only it will be bigger than or equal to every element of A. So let me put the elements of A are ending here. Okay. So let me put the alpha here. Okay. So geometrically, this is the picture. If I pick up any point which is in X here, X which is in A, then the number alpha is bigger than or equal to X. The number alpha is bigger than or equal to X. Okay. Such a number alpha is said to be an upper bound of the set A. Okay. So if I want to write this statement, alpha is an upper bound of A using quantifiers, how will I put that? This simply says for every element X in A, alpha is bigger than or equal to X, or X is less than or equal to alpha. So using quantifiers, I can write this as, using quantifiers, I can write this same statement as, for every X in A, for every X in A, X is less than or equal to alpha, or alpha is greater than or equal to X. You can put it in either way. Okay, it means the same. So this is the meaning of the statement alpha is an upper bound of A. Okay. Now one thing to note here is, if I have one upper bound alpha, then any number which is bigger than alpha, I can pick up alpha 1 here on the number line, I can pick up alpha 2, I can pick up some other number, say q. So if alpha is an upper bound of a set, then any real number which is bigger than alpha is also an upper bound of the set. Okay. So if a set is having one upper bound, it is going to have infinitely many upper bounds, because after alpha there are infinitely many real numbers here on the number line where I'm marking right now. Is it clear? So upper bound need not be unique. A set, if it is having one upper bound, it will have infinitely many upper bounds. All right. Now what is the negation of this statement? What is the negation of this statement which I've written using quantifiers? Okay, when will I say that alpha is not an upper bound of A? That means I have to look at the negation of this. And in the foundations topic, we have already seen how to negate statements having quantifiers. So the negation of this would be, universal will turn into existential. There exists X in A such that X is not less than or equal to alpha. Now by law of trichotomy, what I have, either X is equal to alpha, or X less than alpha, or X is bigger than alpha. Okay. Now X less than or equal to alpha is not true. That means equal to is not true and less than. So both these conditions are ruled out. So this is false, meaning the only possibility now is X is bigger than alpha. Okay. So the negation of this statement is this one. So when I say that alpha is not a upper bound of the set A, what I mean is, I can find one point X in A which is bigger than alpha. Okay. I can find one point X in A which is bigger than alpha. That's the negation of the statement using quantify. And I can write this as, and this is called, this is when alpha is not an upper bound of A. Okay. So alpha is not an upper bound of A if there exists at least one point in A. There exists an element X in A such that X is bigger than alpha. So in this case, we can say that alpha is not an upper bound of A. Now, if you look at the set A that I considered in the beginning, it had the elements 1, 2, 3, 4. The number 2 here, is not an upper bound of the set A. Why 2 is not an upper bound of the set A? Because I can find a number 3 in the set which is bigger than 2. Okay, so 2 is not an upper bound. 2 is not an upper bound of A. Why is that? Is I can find a element 3 in A such that 3 is bigger than 2. Okay, I hope this is clear. So this is when you say that alpha is not an upper bound of A. Okay, I hope it's geometrically. If I want to say that alpha is not an upper bound of A, what do I mean? Okay, again I will draw a number line. Okay, again I will draw a number line, and I will mark some points of A in red. So let me mark few points of A in red. So supposing this is my set A, okay, which is in red, those are the points of A. Just assume that those are the points of A which are shaded in red. And now supposing I have a alpha here, okay, supposing my alpha is lying here. This alpha is not an upper bound of A. Okay, this alpha is not an upper bound of A. Why is that? Because there are so many points here in A. If you see, if you pick up these points here, then you can definitely find at least one point x in A which is bigger than alpha. Okay, so for that reason, this alpha is not an upper bound of A. So in simple words, geometrically, if you want to say alpha is not an upper bound of A, you should be able to find elements of the set A on the right hand side of alpha. Okay, so then you can say that alpha is not an upper bound of A. Okay, for example, let's take one more set. Look at the set B, which is set of all real numbers which are lying between 0 and 1, which are strictly lying between 0 and 1. So let me put it on the number line. 0 is here, 1 is here, and all the numbers which are bigger than 0, 0 is not included in this set, and all the numbers which are less than 1, again 1 is not included in this set. Okay, so all these are the elements of the set B here. Okay, then can we list some upper bounds of A? Sorry, B. One is an upper bound of B, and any number bigger than 1 is going to be an upper bound of B, because every element of the set B is less than 1, right? From here it's quite clear that every element is less than 1. So 1 is a upper bound, and if you pick up any number, say 50 or 5 lakhs, okay, even this number is an upper bound. Even the number which is closest to 1, let's say 1.1, you can say, even this is an upper bound of the set B. Okay, so upper bound of a set is not unique. If you have one upper bound, then you can have infinitely many upper bounds. Okay, so let me put a remark here. If alpha is an upper bound of A, if alpha is an upper bound of A, where A is any non-empty subset of R, and you have a number alpha dash which is bigger than alpha, okay, then the number alpha dash is also an upper bound of A. Okay, so alpha dash is also an upper bound of A. Okay, I hope that's clear. Next, I have a definition which says supposing I have a non-empty subset of R. Okay, let A be a subset of R which is non-empty. So A is a non-empty subset of R. Okay, then this non-empty subset A is said to be bounded above. This set A is said to be bounded above if there is a real number alpha which is an upper bound of A, which is an upper bound of A. Okay, so any set which is having an upper bound is said to be bounded above. Okay, any set which is having an upper bound is said to be bounded above in R. Okay, I forgot to mention the word bounded above in R. Okay, so whenever I say a bounded set, in R, that means there is a real number which is an upper bound of that set. Okay, so using quantifiers, how can I say this? Using quantifiers, a subset A of R is bounded above if and only if. Another way of writing this is, you should be able to find one alpha such that for every element in A, that alpha is bigger than or equal to that element. Okay, so there exists an alpha in R such that for all x in A, for every x in A, x is less than or equal to alpha. That means alpha is an upper bound of A. So there is a real number such that this means alpha is an upper bound of A. Okay. So when we will say that the subset A of R is not bounded, for that you will have to simply negate this, and we have already seen how to negate statements using quantifiers. Okay, so this was the idea behind doing the first chapter statements which I had done for you all. Okay, so a subset A of R is not bounded above if and only if. Let's negate this. That means no matter what real number alpha you take, for every alpha in R, you will be able to find one point in A, okay, which is bigger than alpha. That means there is no real number which is an upper bound of A. Okay, so the negation of this will be for every alpha in R, okay, there exists at least one point x in A such that this statement here is not true. Okay, such that x is bigger than alpha. And that is when you say that a subset A of R is not bounded above. Okay, if I want to say that a set is not bounded above, what do I mean when I say this geometrically? Okay, can you all visualize what this means? How will the set A look like if it is not bounded above? For that, let me draw a number line. Okay, and on the number line, I will mark the set A. Okay, I will mark the set A. Supposing my set A is this. Okay, some points here, maybe there is a gap here, and these are the points. Then I can pick a alpha here, okay, which is bigger than all the elements of A. In that case, A would be a bounded set. So for A to be unbounded, or A is not bounded when the points of A will keep on going this way. Okay, so it will be impossible for you to find an upper bound for the set A. They will keep on moving. So no matter which point here you pick up, if you pick up any point here in between, then if you pick up any alpha here, this alpha will not be an upper bound because there are points of A here. Okay, there are infinitely many points of A here. So none of the real numbers can be an upper bound of A in this case. So a unbounded set or a set which is not bounded will look somewhat like this. Okay, I hope that's clear. Now let's look at one more example. Supposing I have this example with me, the set A, which is the open interval 0, 1. Okay, open interval 0, 1, and this is nothing but all the real numbers which are strictly lying between 0 and 1, right? So that's the open interval 0, 1. I have introduced the word open interval 0, 1 in the statements chapter. Okay, so I hope you all are familiar with this. Now if you try to look at this, let's look at the upper bounds of this set. Okay, I have this open interval 0, 1 with me. 1 is an upper bound because 1 is bigger than or equal to all the elements of this set. Okay, and then because 1 is the upper bound, all these numbers on the right hand side of 1, they are also upper bounds of the set A, right? Now the question that comes up here is there any upper bound of the set A which is less than 1? Okay, Is there any upper bound of this set A which is less than 1? That is the next question. If you assume that there is any other upper bound here which is less than 1, okay, if you pick up alpha here, then this alpha cannot be an upper bound of A, because there are so many points here which are bigger than alpha of A. Okay, so even if you zoom in there between alpha and 1, okay, I will just zoom in this part, alpha and 1. So alpha is here and 1 is here. Okay, so there are so many points here. Even if you pick, even if this alpha is 0.9, then there are so many points even here. 0.91 is there, 0.92 is there. Even if you say 0.99 is an upper bound, again that is going to be false, because I can again find the midpoint of this number 0.99 and 1, and again I will find point here. Again, if you say this point which I marked just now is an upper bound of A, again that will be false, because here I can find points of A. Okay, so this gives us some intuition that 1 is the smallest upper bound of A, and there cannot be any upper bound of A which is smaller than 1. Okay, so this idea motivates the definition of supremum of a set. Okay, let's see what is a supremum of a set, or least upper bound. Okay, another word is least upper bound. So, it is also, in short, you can also write it as LUB, least upper bound. So I will take a non-empty subset A of R. Okay, so let capital A be a non-empty subset of R. Pause. Continue. So let capital A be a subset of R which is non-empty. Non-empty meaning there is at least one point in the set. Okay, then a real number alpha is called the supremum, or another word is least upper bound of A if the following conditions are true. Okay, so when I say least upper bound, from the word itself it is clear that number has to be an upper bound first, and it has to be least of all the upper bounds. Okay, so the first condition for alpha to be called a supremum or the least upper bound of A is alpha is an upper bound of A. Alpha must be an upper bound of A. All right, and secondly, it has to be the least of all the upper bounds. Okay, this alpha has to be the smallest of all the upper bounds for it to be the least upper bound. Is it clear? That means when do you say that something is least? If you take any other upper bound, then it has to be bigger than or equal to alpha. Then only alpha will be the least, right? Okay. So second, to say that alpha is the least, if beta is any other upper bound, if beta is any other upper bound of A, if beta is any other upper bound of A, then alpha must be less than or equal to beta. That means if I have a non-empty subset A of R, then a real number alpha is called the supremum or the least upper bound of A if alpha is an upper bound of A, the first condition. Secondly, if you pick up any other upper bound of A, then that upper bound has to be bigger than or equal to alpha. Okay, so indirectly I am saying that alpha is the smallest upper bound of A, that is the least upper bound of A, and another word for this is supreme. Okay, I hope this is clear. Now let's look at some examples of sets, and we'll try to find the supremum of those sets. Okay, so uh, okay, find the supremum of the following sets. or you can also say least upper bound, LUB. Okay. The first one, I'll pick up the same one that I started with in this video. Let A be equal to the set 1, 2, 3, 4, a finite set having 4 elements. Okay. Clearly 4 is an upper bound because 4 is bigger than or equal to all these elements. So since 4 is bigger than or equal to 1, 4 is bigger than or equal to 2, 4 is bigger than or equal to 3, and 4 is bigger than or equal to 4, it is clear that 4 is an upper bound of A, right? Now I want to show that 4 is the least upper bound of A, that is 4 is the supremum of A, okay? So we need to show that 4 is nothing but least upper bound of A. This is how you write, in short, least upper bound of A, or you can also say supremum of A. Okay, I'll keep on switching between these notations, okay, so that you all are comfortable with both the notations. So how do we show that 4 is a least upper bound? If you go by definition, if you go back and see the definition, that says first condition is 4 is an upper bound, that is already true. If you take any other upper bound of A, then that has to be bigger than or equal to this 4. Then only 4 will be the least upper bound, right? So let beta be any other upper bound of A. Let beta be any other upper bound of A. Okay. That means beta will be bigger than or equal to every element of A, right? In particular, 4 is also an element in A, and beta is bigger than or equal to every element of A. So beta will be bigger than or equal to 4. That means what we have shown here, 4 is an upper bound, first step. Secondly, okay, this is the first step. Second, if beta is any other upper bound of A, then beta is greater than or equal to 4. So finally, we have shown that 4 is the least upper bound of A, or the supremum of the set A. Okay, because the supremum 4 was in A and A was a finite set, it was very simple. It's a trivial case. Okay, so let's look at one more example. Let me take B equal to closed interval 0, 1. Okay, so all the numbers which are lying between 0 and 1, and they can be 0 and 1. Okay, clearly 1 is an upper bound, right? So by definition itself, this says x is less than or equal to 1, then only the element x will come in B. So by definition itself, x is less than or equal to 1 for all x in A, right? That means 1 is an upper bound of A. B. Sorry, B, I'm saying A, it's actually B because my set is B. So 1 is an upper bound of B. Okay. Now, to show that 1 is the least upper bound, what we have to do? Assume that there is some other upper bound. So take some other upper bound of B. Okay. So let some other notation, let's say theta be any other upper bound of B. Okay. That means this theta will be bigger than or equal to every element of B, right? In particular, 1 is also an element of B, correct? So in particular, 1 belongs to B, and theta is bigger than or equal to every element of B. That means theta will be bigger than or equal to 1. So what did we do? We showed that 1 is an upper bound, and if theta is any other upper bound, theta is bigger than or equal to 1, and therefore 1 is the least upper bound of the set B. Okay, so we are using the definition of the upper bound or the supremum, and we are finding the supremum of the given sets. Okay, you look at the set of natural numbers. Is it possible to find an upper bound for this set? Is it possible to find an upper bound for this set? This keeps on going. Supposing alpha is an upper bound. Let, if possible, alpha is an upper bound of n. Let alpha be an upper bound of n. Okay, then alpha must be somewhere here on the real line. So if so what you can do after this, you can always find a natural number, right? No matter how big this alpha is. Okay, so that won't be possible. If alpha is a natural number, then you pick up alpha plus 1. Even if alpha is not a natural number and it is lying between two natural numbers this way, you take the greatest integer function of alpha, so you'll be here, and then you add 1 to it. Okay, so what you can do, you can pick up the point x is greatest integer value of alpha and you add 1 to it. This will definitely be a natural number, and this x will be bigger than alpha, right? So that's not possible. Okay, so that's a contradiction. So alpha is not an upper bound of natural numbers. So natural numbers, this set is not bounded above. Okay, so this set is not bounded above in R. Okay, I hope that's clear. Next, so if I take one set, okay, if I take one set A which is bounded above, okay, let A be a non-empty subset of R, non-empty subset of R, okay, and let alpha and beta be least upper bounds of A. Supposing there are two upper bounds of A, okay, then what we can prove is these two upper bounds will be same. That means if you take any non-empty subset of R, okay, if you take any non-empty subset of R which is bounded above, of course, then only I can talk about a least upper bound which is bounded above. I'll just put it here, which is bounded above, okay, then both the least upper bounds will be same. That means the least upper bound is always unique if it exists. Okay, so let's try to prove that alpha is equal to beta. Okay, I will use one of the properties which I have discussed in the previous video. Okay, now alpha is the least upper bound of A and beta is also the least upper bound of A. This data I have with me. Okay, alpha is the least upper bound, meaning what? Alpha is an upper bound and it is the smallest upper bound. Again, beta is an upper bound, not B, A here. Again, beta is an upper bound of A and it is the least upper bound of A. That's what I know from the given information, right? Now, what I'll do, first I will consider alpha to be the least one here and beta to be an upper bound here, because beta is also an upper bound, right? Now, alpha is the least upper bound of A and beta is an upper bound of A. I will use only the upper bound property of beta, is an upper bound of A. Okay, so alpha being the least and B being any other upper bound, that means alpha must be less than or equal to beta, because I'm assuming that in this case alpha is the least upper bound. Okay, so similarly what you can do also, alpha is an upper bound. If it's a least upper bound, then definitely it's an upper bound of A. And now I take beta as the least upper bound because beta is given to be least upper bound and beta is the least upper bound of A. And because alpha is the upper bound and beta is the least upper bound, that means beta must be less than or equal to alpha. And I did one of the properties in the last video which said if A is less than or equal to B and B is less than or equal to A, then A is equal to B. So by 1 and 2, what I can say is alpha is same as beta. Okay, so if you take a non-empty subset of R which is bounded above, then it is going to have a unique supremum or least upper bound. It cannot have more than one upper bounds. Okay, these are my references. Thank you.